Hello students. In your previous lecture we have discussed about the various power stages involved in an induction machine. In your today's lecture what are we going to do is that basically we'll derive the expression of your electromagnetic torque so as to obtain your torque slip characteristics. See, now this torque slip characteristics is very important, very important. You must be able to understand this torque slip characteristics very properly, conceptually, so that you'll be able to solve various numericals. Not only you'll be able to solve the numericals, you'll be able to understand your machine, how actually, how practically, how physically it is operating. So you will be able to understand that thing. So I'll request you all to pay much attention on this topic because this is very important topic. First of all, we'll derive the expression for electromagnetic torque. Thereafter, we'll move towards your torque slip characteristics. See, as you can see here, so I'll straight away go to the previous lectures slides because I just wanted to show you the relation between, as I've told you, that what is the relation between power, torque, and speed. We know that power, active power P, is equal to torque into omega, where omega is nothing but your speed in radian per second. So you can convert that omega, obviously always you can convert that omega into rotation per second also and into rotation per minute also, because you know that omega equals to 2 pi small ns, where small ns represents your speed, synchronous speed in rotation per second. Capital ns, if you want to convert, then you can always write omega equals to 2 pi capital ns divided by 60, where capital ns is nothing but your speed in synchronous revolution per minute. Okay, so now I'll show you that expression also, what we have previously derived. See here. Here you can see that this rotor power input is given by this expression. Now, as I've told you, this rotor power input is nothing but your PAG, that is your air gap power. So you can see the electromagnetic torque corresponding to this rotor input. If you want to develop the electromagnetic torque corresponding to this rotor input, that is PAG, then you are taking your synchronous speed. So this thing is very important, keep in mind. If you want to derive your electromagnetic torque with respect to your electromagnetic torque corresponding to your air gap power, then you will always take this synchronous speed. Okay, and if you want to derive your electromagnetic torque with respect to your shaft power or with respect to your rotor power, then you will always take this rotor speed, this n. So this thing is very important, you must be very clear about this thing. So always remember, whether you need to derive, if you are deriving your electromagnetic torque, obtaining your electromagnetic torque with respect to your synchronous speed, I mean with respect to your air gap power, then always take synchronous speed. And if you are deriving, if you want to obtain your electromagnetic torque with respect to your shaft power output or rotor power output, then always take your rotor speed. Okay, this should be very clear. So I'll go back again to today's lecture. See here, now basically what we need to derive is that we are deriving basically our electromagnetic torque. See, in a motor, see, this is how a motor is being represented. This is a motor. See, in a motor basically there are two torques. One is your electromagnetic torque, which is denoted by TE, this thing electromagnetic torque, and one is always your opposing torque. Now if the motor is operating on no load, then there is, I've already told you that then in case of no load there is always one opposing torque. What is that? That opposing torque is basically equal to your torque required for your frictional torque. Okay, if you are talking about a practical machine, then there'll be always a frictional torque opposing the electromagnetic torque developed. Now how this electromagnetic torque is developed, we have already seen that whenever there is a relative speed between the synchronous speed, stator field, and the rotor speed, then induced EMF will be developed, and hence a current will start flowing, and hence an electromagnetic torque is developed, which will rotate the rotor in the direction of NR. See, NR is nothing but your rotor speed direction. See, if so in this case your motor is rotating in clockwise direction with speed NR. So your electromagnetic torque will also be in clockwise direction, and your opposing torque will always oppose your electromagnetic torque. And then if the motor is on no load, then this opposing torque is equal to your frictional torque. And if the motor is load, motor is loaded, if there is you are providing some load on the shaft, then this opposing torque is basically the sum of frictional torque plus the external load that you are applying on your shaft. That will be your opposing torque. Suppose external load that you are applying on the shaft is, suppose torque corresponding to the external load applied on the shaft is TL, then, and torque corresponding to friction is TF, then total opposing torque will be TF plus TL, and the total electromagnetic torque developed is TE. And always keep this in mind, you must have seen this all while you were studying your DC machine also. The difference between this electromagnetic torque and the opposing torque is nothing but your acceleration. Are you getting my point? what what am I saying? Kindly listen to this very carefully, because this is very important. See, your electromagnetic torque is developed in clockwise direction, and your opposing torque, that is your frictional torque plus your load torque, that is providing force in the opposite direction, anti-clockwise direction. So if suppose your electromagnetic torque is greater than this opposing torque, then the motor will rotate in clockwise direction. If opposing torque is greater, then rotor will rotate in anti-clockwise direction. So this is the difference between these two torques, TE, the torque generated electromagnetic torque, and the opposing torque. The difference between these two torque is basically the difference is between them is basically resulting in your acceleration. More the difference, more the rotor will accelerate. Lower the difference, lower the, if the difference is negative, say if suppose T opposing is greater than T electromagnetic, then you can say that the motor will instead de-accelerate, and if T is greater than electromagnetic torque is greater, then it will accelerate. See, these things will be coming, you'll be seeing when we obtain your torque slip characteristics. So these things are very important, so pay attention on this thing. And also I'll request you to go through these things and understand these things again and again. So go through these lectures again. Okay, so now we were talking, see, this is written, this total opposing torque is nothing which is the sum of frictional torque and net mechanical torque. This mechanical torque is nothing but the torque required for rotating your external load that is attached on the shaft. Okay, that is your mechanical torque. Okay, so this thing is very important. So now this total opposing torque should be equals to electromagnetic torque. And what is your electromagnetic torque? What is the value of your electromagnetic torque? We know that if we are taking electromagnetic torque with respect to the gross power output, see this thing here, P gross mechanical power developed, overall mechanical power developed at the shaft. This overall mechanical power developed at the shaft is given by what? 1 minus slip times PAG. This is your gross mechanical power developed. This is given by this formula, 1 minus S is nothing but your slip, 1 minus S times PAG is your air gap power. This, so 1 minus S times your PAG. So I've told you that when we'll take this power, if you want to derive your electromagnetic torque corresponding to this power, then what speed are we going to take? We'll basically take your speed of the rotor, that is NR. And if you want to derive your electromagnetic torque corresponding to this power, then you will basically take the speed which will take is your synchronous speed. Okay, so this thing again you should be very clear. So see, now we are taking 1 minus S into PAG, we are taking this power PAG. So what speed are we going to take? NR. So that is why we are dividing by torque is nothing but we know that power divided by omega R, and omega R can also be written as 2 pi NR. Now this NR is what? Your rotor speed. So NR could also be written as 1 minus S into NS. We all know that rotor speed could always be written in terms of synchronous speed. See, this NR, always keep in mind, this NR is rotation per second. Small NR is rotation per second. Capital NR is rotation per minute. So don't get confused in while solving your numericals. You should be very careful about whether you are writing. If you are writing here rotation per minute, then you need to divide it by 60. Okay. So this thing should be very clear. Okay. Now, what else? Now you can see that NR is also NR could also be written as 1 minus S into NS. Okay, 1 minus S into NS. So substitute this value of NR over here. So you can see 1 minus S cancels out, and you will get what? PAG divided by 2 pi NS. This is also electromagnetic torque. So now, but this electromagnetic torque I've told you is corresponding to your PAG, air gap power. And you can see that if you take your electromagnetic torque corresponding to your air gap power, then what is the speed that should be taken? This is NS and not NR. For PAG it should be NS. For this is what this is PG, P shaft. For P shaft it should be NR, and then PAG it should be NS. So these are the formula for developing your, for obtaining your torque expression. Always be careful about this thing. Okay, now, so one more thing, this is also important. So you can say that this electromagnetic torque is equal to PAG. Here you know that, look at the arrow here, you know that TE, electromagnetic torque, is equals to PAG divided by 2 pi ns. When we obtain, when this expression is written, that means the unit of TE, that is the electromagnetic torque, is in Newton meter. Its unit is in Newton meter. But if we write this TE equals to PAG, then the unit of torque, this TE can also be written as equal to PAG. Then its unit will be in synchronous watt. So suppose somebody asks you to find out the electromagnetic torque, whose unit is in synchronous watt, then there's no need to divide it by 2 pi ns. Directly PAG is also a measurement of electromagnetic torque, but that electromagnetic torque unit will be synchronous watt. Now if you want to obtain electromagnetic torque in Newton meter, then divide this PAG divided by 2 pi ns. So this PAG divided by 2 pi ns will give you electromagnetic torque in Newton meter. So this thing is also very important. Somewhere in numerical you can always see these things while drawing your circle diagram. This is which is not right now, which is not in your syllabus. In circle diagram now, this thing is very important. They are taking this synchronous watt into use for just simplification of calculation. There's nothing much in this. Now we know that this electromagnetic torque value is equal to what? PAG divided by 2 pi ns. Now we need to derive the expression for electromagnetic torque. So what are we going to do? We'll substitute the value of this PAG. Now we know that PAG is nothing but thrice of I2 dash ka whole square into R2 dash divided by S, divided by this 2 pi ns. 2 pi ns. This is what your torque expression, and this I2 dash is given by this expression. So where am I from where I am getting all these expressions? This, remember, we have developed one equivalent circuit of an induction machine, Thevenin's equivalent circuit of an induction machine. We have replaced that stator body with a Thevenin's equivalent circuit. So from there I am getting this expression. I'll take you to that slide so that you can see again, because see, I'll request you to go back through all these slides again and again, so that you can relate much more in a more proper way. So this thing, see, this was the equivalent circuit which we have developed. Now this was the VTH. Now what is VTH? VTH is nothing but V1. V1 was the source voltage, divided by R1 was synchronous resistance, and X1 was synchronous stator resistance and stator leakage reactance. XM was for magnetizing reactance. Now this thing VTH will not do. From this expression you can see one more thing, that as we all know that this XM, value of this XM is very greater, much greater than this R1 and X1. This value of these R1 and X1 are very small values. Why? Because winding resistance will design the winding accordingly. We'll take those windings whose internal resistance should be very small, and we always want our internal leakage reactance should be very small. So these values are very small, while this thing XM is large. Compared to them, it is very large. So what you can do is, for simplification, sometimes mostly they'll say that neglect some, in some numericals you'll find that a term is written, a statement is written, that neglect stator impedance. Now what are they basically trying to tell you is that they are telling you that neglect stator impedance means they are telling you that this R1 and X1 are very small, so you can neglect them. Now how do, if this is neglected, then X1 plus XM is approximately, they have taken as XM. Why? Because X1 is, they are telling that it is very small, so X1 plus XM is approximately replaced by J times XM. Now R1 plus J times X1 is again approximately replaced by J times XM. R1 is again neglected. So put this thing 0, this R1 0 and X1 0. So you will get V1 divided by JXM into JXM. So VTH, in that case, whenever a statement is written that neglect the stator impedance, then in that case directly you should put R1 and X1 as 0. So what are we going to get? You're basically going to get this thing, VTH equals to V1. Okay, why JXM and JXM will be cancelled out. VTH is equal to directly V1, and this ZTH, if this and this is neglected, Suppose this thing is neglected, don't in this expression don't put it in 0. You can jx x1 plus xm, you can put it jx1, and then r1 plus jxm, you can substitute jxm, then this jxm and this jxm will cancel out. So directly your zth is equals to r1 plus jx1, comes out to be r1 plus jx1. Now we know that r1 and jx1 are means r1 is also very small and jx1 is very small. So this rth and xth you can substitute directly with 0. So whenever they say that neglect stator impedance, then what all things you need to do in this circuit, equivalent circuit? Replace this VTH directly by V1, that is the source voltage. Replace this RTH directly 0, XTH directly is 0. Now see, the circuit is very means circuit becomes very easy. As soon as they say that neglect this stator impedance, circuit becomes very easy. Directly V1, the applied voltage, and then these are the rotor parameters which you need to take into account. Okay. So this and why can we do the, we can also, there's no point, there's no harm in doing all these things. Why? Because we know that the stator impedance are as such very low, so not much difference will come even if you ignore all these stator impedances. So directly you can substitute VTH equals to V1, RTH and XTH equals to 0, and then you can find out the expression. Now from here we have find out this expression, I2 dash equals to VTH divided by root of RTH plus R2 dash ka whole square plus XTH plus X2 dash ka whole square. This thing we found from this equivalent circuit. You found this value of R2 dash. Why? Because I2 dash we will be using in those for calculating the expression of electromagnetic torque. Now we know that PAG, from here only I have told you that PAG value is what? Thrice of I2 dash ka whole square into R2 dash divided by S. Okay, I2 dash ka whole square into R2 dash divided by S. This is what we are replacing over there. This circuit is basically single phase circuit. Now we need to take it over there. While developing your electromagnetic torque, we are basically taking three phase. We are basically deriving the electromagnetic torque for a complete motor, so we'll be deriving for three phase. So now we'll go back to that so that I can tell you here. Now you can see that this TE is what? TE is PAG divided by 2 pi ns, and you know that PAG is nothing but thrice of I2 dash ka whole square into R2 dash divided by S. Why? Because of why this thrice? Because now we need to take for three phase. This is phase current. These all things you need to remember while solving numericals. And I2 dash from there, from that equivalent circuit, we have obtained I2 dash equals to this much. Okay. So by solving this thing, by substituting I2 dash equals to this thing in this expression, you will get the expression of torque equals to this much. Thrice of VTH ka whole square into R2 dash by S divided by 2 pi ns RTH plus R2 dash by S ka whole square plus XTH plus X2 dash ka whole square. This is your electromagnetic torque developed, expression for your electromagnetic torque developed. Now you can see from this thing that this electromagnetic torque developed is proportional to only your slip, is dependent only on your slip, while all the parameters are mostly constant. So we'll basically discuss about these things, torque slip characteristics. Now we have derived this electromagnetic torque expression. From here we'll draw the torque slip characteristics, and we'll see various concepts of an induction machine. So in your next class, next lecture, we'll be continuing from here. Thank you very much.